Okay, quick video for section 3.4, which is another short section. Yep, some basic stuff on page 1, and then problems for you to try on the back on page 2. So we have radians in our toolbox now, and they become particularly important for some of the things we're doing here. And they work very nicely when we start talking about lengths of arcs on a circle and areas of what we call sectors of a circle. So here's our picture right here. So we have a central angle, theta, there in the circle. These, of course, are both radii, so they're both length r. And s is the variable that's typically used for the length of an arc. All right, so what's that distance? Well, we already saw this. This is our definition of angles in radians, and s and r were the radius and the arc length that went with it. So turning that around, we quite easily get s equals r theta. The arc length is just the radius times our angle theta, but this is a big deal in radians. And area actually uses the formula for the area of an entire circle, which is pi r squared, and basically takes the appropriate fraction of it to get just the area of this region here. All right, so 1/2 r squared theta, but again, theta in radians. All right, so you can do some real simple computational problems here. We got a circle, radius 10 inches, a central angle of 120. So find the arc length and the area that go with that thing. So we're just going to look at the filled in version here rather than writing it all out. This would be your, picture of what's going on. So circle, angle, radius of 10. So what is this arc length from side to side on that angle? All right, well, you can just use s equals r theta, provided theta is in radians. So we do our conversion. There it is in radians. S equals r theta, multiply them out. There's your answer. And area is really just a plug and chug thing. Once you got your angle in radians, plug it in the appropriate places, punch it out. There it is. 104.7, and notice inches squared because that's an area. So s equals r theta is about as nice as an equation gets. All right, it has 3 variables, so if you know 2 of the 3, you can figure out the third. All right, so we have a Ferris wheel. When it rotates 50 degrees, a car goes around 70 meters. So in other words, it traces out a circular path that is 70 meters long. So that's this sort of idea. The Ferris wheel rotates 50 degrees, and car on the outside of this circle then travels 70. So in other words, s is 70, and it's in meters. Theta is 50 degrees, which, if we're going to use s equals r theta, needs to be put into radians. So here it is in radians. And we can just plug them in. So here's s, and there's the r we don't know, and here's our theta in radians. So do a little solving, and out comes your answer. And it would be in meters, as that's the length unit that we have going on here. Example 3. There's a little more to do here, and I think, in fact, that one I'm going to do on the blank version, and we'll actually sketch that out. All right, so we are going to make a sketch. Erie, Pennsylvania is directly north of Columbia, South Carolina, and they're at different latitudes. So what I'm going to do is draw a cross-section of the Earth. So here's the center of, there's the center of the Earth here. The equator is right here, and the North Pole is right here. So an object's latitude is where it's located on the surface, and then the angle that's made from the equator. So if this is Erie, then this angle right here is 34 degrees. Columbia, South Carolina has a higher latitude. It's not the greatest picture, but it makes this angle 42 degrees off the equator. So the equator itself is at 0 degrees latitude. So here's Columbia. So how far apart are these guys? Well, that's like saying if this is S, that the distance between them is S, what's the length on this circle that goes with this angle right here and a radius of 6,400 kilometers? So S equals R theta is all we're talking about, where we know R is 6,400. And theta, well, it's not this theta right here. It's not, oops, it's not this guy. It's this right there. And theta would be, well, just take the difference. 42 degrees minus 34, so theta is 8 degrees. You gotta multiply that by pi over 180 to convert it to radians, which you can punch it out as a decimal or just keep it exact. You can cancel a 4 out of 8 and 180. Get 2 pi over 45. So that would go in, woo, oh, I'm all over it. That would go in for theta. So 6,400 times 2 pi over 45. And if we punch that out to the nearest kilometer, 894. Now that only works for two cities that are directly north and south of each other. If they're at all east or west, you can't do a slice through the earth that goes through the center and is perpendicular to the equator and gets both of those cities involved at the same time. Big Rapids is in the 44, 43 degrees range when you drive to up north. Before you get to the bridge, I forget where, you pass the 45 degree mark where you're halfway between the North Pole and the equator. All right, so the remainder, the sketch is much nicer in the filled in version of the notes, as you can see right here. The second page is group exercises, all right, using these properties and figuring some things out. I feel like the solutions are all written up pretty well, so it'd be a good idea for you to just try them and see how they go. Some of them are asking for area, some of them are asking for distances. Some of them have just a few other little extra things you gotta pay attention to, distances to add in for perimeters and things like that. Why don't you go ahead, try those group exercises, see how they go, and you've got the filled in version, and you can check answers and whatnot. So, but that's it for 3.4. 3.5, we will have similar things, but they will start moving in time, and that will present some other details we need to manage. But for 3.4, that is it.